In this video, I'm going to discuss a quiz that we had that was covering chapters 3, 4, and 5. This video is going to discuss questions 6 through 10. Water is placed in a sealed container and put into a refrigerator. The water freezes and the container cracks open. We're asked to assign Q and W for this process, where water is the system. This topic is in chapter 5. We're assigning signs for heat and work, Q and W, for the transfer of those based on a scenario. A description is given and we have to ask what does it mean in terms of Q and W for the system. Since the water is the system, let's see first of all what happens. It goes from being a liquid to a solid. The enthalpy change for this is negative. It's an exothermic process. Heat has to leave the liquid in order to transfer to a solid. Q is negative. The volume is increasing. How do I know that? Because it went from a liquid to a solid and it cracked open the container. Work is being done on the surroundings. Work being done on the surroundings has a negative sign. This one's a fill in the blank and it's involved enthalpy changes and how do we account for those? Clearly we have to be able to rank enthalpy values and compare copper solid at 30 degrees and copper solid at 90 degrees. And then be able to compare and explain those in terms of potential and kinetic energy. When ranking these, the copper solid is at a lower enthalpy value than at 30 degrees is at a lower enthalpy value than the copper solid at 90 degrees. We would have to add energy to take it from 30 degrees to 90 degrees. So therefore the copper solid at 30 has the lower enthalpy value. Is that explained best in terms of potential energy or kinetic energy? Well, the phase is the same in both cases. It's a solid in both cases. The volume might change a little, but remember that a probe of the kinetic energy is the temperature. The temperature reflects the average kinetic energy of the substance. So the copper solid at 30 degrees has the lower enthalpy, and that's best explained by the kinetic energy. When we went to 30 degrees to 90 degrees, the kinetic energy was increasing. Potential energy probably stayed about the same. In this one, we have a chemist adding 2 grams of sodium hydroxide to a 50 milliliter volumetric flask, filling it up to the line with water, and then transferring 20 mils of this to a beaker. That subsequent solution then is combined with some sulfuric acid, and we're asked how much sulfuric acid is needed to neutralize that solution. This really has 2 different parts. The first part refers to an idea in chapter 4, which is preparing a solution. The second part now is solution stoichiometry. So let's consider the preparing a solution first. We're taking 2 grams of sodium hydroxide. We can convert that to how many moles it is. What's happening to the solid? After placing it into the volume flask, we're filling it up to 50 mils. That's making the initial solution. Was all of its solution used in the subsequent analysis? No, only 20 mils of it were used. So therefore, even though we may initially have 0.050 moles of sodium hydroxide in the first solution, not all of those are used in the subsequent analysis. Only 20 out of the 50 mils are transferred, so therefore only 40% of the moles were transferred. So the first thought is that when we do the subsequent neutralization reaction, we have 0.02 moles of sodium hydroxide that need to be neutralized by the 0.20 molar sulfuric acid. Here's a balanced chemical reaction for the neutralization reaction. I see in the H2SO4 I didn't include a subscript, my bad on that. So we have figured out though how many moles of sodium hydroxide were involved in the reaction. We want to make sure that we have it balanced, and we see that we have 2 sodium hydroxide for every 1 sulfuric acid. So therefore on the change line, if we have 0.02 moles of sodium hydroxide to consume, it requires 0.01 moles of the sulfuric acid. If we have the provided sulfuric acid solution, which is 0.20 molar, that's 0.20 moles of sulfuric acid per liter. We don't know how many liters we need, but we know, based on our BCA table, we need it to equal 0.01 moles of sulfuric acid. Our quick calculation says that that is 50 mils of the sulfuric acid that we need to neutralize the sodium hydroxide. So again, we had two ideas here. The first was preparing a solution, and the second was now taking a portion of that solution and having it involved in a neutralization reaction where we had a balanced chemical equation and we used a BCA table to keep track of what was going on. In this one we have an acid-base calorimetry experiment involving sodium hydroxide and HCl. This is an experiment that you're going to do in lab or have already done. The notion is that when you combine sodium hydroxide with HCl to produce water and the salt sodium chloride, there's heat involved with that. And in fact, it's an exothermic reaction. When you have 1 mole of sodium hydroxide, 1 mole of HCl, it produces 56 kilojoules of heat. Heat's going to be produced in this experiment until the limiting reactant is used up. What's the heat going to do? It's going to raise the temperature of the solution. So we can use the specific heat of the resulting salt solution, the amount that we have, its mass, and see how the temperature changes based on the heat that we had that was provided by the reaction. Will the initial temperature be important? Yes, because we're looking at the change in temperature. Will the moles of a limiting reactant be important? Absolutely. The reaction only goes to the extent that we have the limiting reactant present. Will the volume of the salt solution be important? Yes, because as we see within our specific heat calculation, we need to know the amount of that solution. Will the specific heat be important? Yes, because again, that shows up in the specific heat calculation. The one that does not is moles of excess reactant. The moles of excess reactant was, in a way, it did not matter within this one. The reaction only produces heat based on the amount of the limiting reactant. Which of the following is a salt produced by combining a strong acid and a weak base? We saw in the previous question that sodium hydroxide combined with hydrochloric acid produced water and a salt. NaCl is a name for what we might everyday call salt, but in any case when we have a neutralization reaction, the product of that, the resulting ionic compound, is something that we'd call a salt. So sodium chloride forms when we're combining a strong acid with a strong base. Sodium hydroxide and hydrochloric acid produce the salt sodium chloride. What about potassium nitrate? This is also a salt that is a product of combining a strong acid with a strong base. Potassium hydroxide and nitric acid will produce potassium nitrate as the resulting salt and water. The ammonium iodide, that is a strong acid combined with a weak base. The weak base is ammonia, the strong acid is the HI, the resulting sodium iodide is the salt that we have. So that's our answer. We are combining a strong acid and a weak base. The remaining ones are incorrect. Calcium hydroxide is a strong base, and the strontium acetate, that would be a weak acid, acetic acid, being combined with strontium hydroxide, our strong base.